My talk is on securing cloud data storage for enterprise users, from cryptographic research to system design. So here is the agenda. Introduction, the cryptographic techniques for cloud data security, and followed by SBox, which is our design of a secure enterprise cloud data storage solution, the system, and finally, conclusion. Introduction. Many companies have migrated their data to the cloud because of the tremendous benefits cloud computing can bring to the organizations. In the current COVID-19 pandemic, working remotely is becoming a new norm. This trend will definitely accelerate the process of cloud migration. But how about security? So if we look at some of the recent data breaches, data breach certainly are taking center stage and is becoming a growing risk. So here are some survey results. First, the likelihood of experiencing a data breach for an organization in the 2018-2019 is about 30%, which is very high. And once a data breach happens, it can be very costly to the organization. The average total cost of a data breach is $3.86 million US. So this is on a global basis. In the United States, no, that is the most expensive country for data breach. That can cost on the average $8.64 million US. And moreover, it takes an awfully long time to identify and contain a data breach, on average 280 days. Well, data breach can have huge negative impact on business. So short term, we mentioned it can have huge financial losses, can cause business disruption and compliance issues. And in a long term, the reputation damage can leading to lost business and lost competitive edge for the organization. Well, here is a wish list for data security solutions in the cloud. First of all, we wish to have strong protection and to end encryption. So that is from the data owner's computer, data is encrypted, and so that data is protected all the way during the transit and storage. And data only appear in plain text form after decryption at the receiver's computer. Well, strong security protection is not enough for user acceptance. So the solution should also have good usability. So for example, must be scalable in sharing. When data is encrypted, data can still be shared among authorized users, and scalable in search and even computation when data is encrypted. Lastly, in terms of the operational overhead, the cryptographic key management, including user revocation, must be simple and efficient. Well, next, I'd like to take a quick overview on some of the cryptographic techniques in the recent literature. Okay, so a lot of research has been done for, especially in the crypto community for data security and privacy protection. So I will focus on three categories of the cryptographic techniques. The first category is attribute-based encryption, ABE in short, and specifically for ciphertext policy attribute-based encryption. And secondly, we'll take a look at the literature's searchable encryption, or simply SE. And also, there are a large body of research findings, computation over encrypted data, such as fully homomorphic encryption. So because of the time limit, I will just focus on ABE and SE on the first two topics. Well, the CPABE is a promising technology for protecting data security in the cloud. Why it is promising? Because it enjoys a number of nice features. All right. First, in the CPABE system, the key generation center, KGC, will generate a decryption key for user. All right. That decryption key is associated with the attributes of the user. For example, Charlie has the identification number, has the company he works for, and position in the organization. Those are examples of his attributes. And those attributes are cryptographically bound to his decryption key. And the data owner, when he wants to encrypt the data, upload to the cloud, he can formulate an access policy. All right, this policy is associated with the ciphertext. The example access policy is, this is the identification number. So somebody with such a identification number is able to decrypt this ciphertext, or somebody with the attribute general hospital and the cardiologist is also able to decrypt this ciphertext. So if we look at these two particular users, Charlie has the identification number, he's able to decrypt. Alice has the attributes general hospital cardiologist, so she's also able to decrypt. Other users' attributes does not satisfy the access policy, are not able to perform decryption of the data. Right. Also, it is designed for scalability. All right, because it is a one-to-many public key encryption, so which is different from the traditional public key encryption techniques. The traditional encryption techniques is one-to-one, so ABE is one-to-many. Well, so despite of its nice features, the basic version of ABE has a number of limitations. Right, the most important critical limitation. The first is how to perform user revocation efficiently. So when a user left organization, even though the user still have a copy of the decryption key, he should not be able to use the key to continue to decrypt data. Right. So this is the purpose of user revocation. And the second is, if we look at the access policy, because the access policy is a combination of the attributes. So the access policy may leak sensitive information about the data. Data is encrypted, but access policy may leak sensitive information. So in this example, looking at the access policy, and people can deduce that somebody with such a identification number may suffering from a heart problem. Right, so that is significant information leakage. Well, on the user revocation, in the literature, a lot of existing solutions, but basically those solutions can be divided into three categories. The basic solution was proposed in 2001. All right, so the solution is to divide your time into different intervals. For example, a day is an interval, and associate ciphertext with a timestamp. So this T is the time interval, right? And KGC periodically updates users' decryption keys over a private channel. So at the beginning of a time interval, the KGSA will send in the new decryption key to decrypt new ciphertext. And if user is revoked, he will not receive the new decryption key. The second approach is tree-based approach. Follow the same principle, associate the ciphertext with a timestamp, but the KGSA broadcasts key updates to users over a public channel. Now, the basic solution is over a private channel. So that is a very strong assumption, a big demand on the users. The tree-based solution relaxes that assumption over public channels, but users are still involved in the revocation process, have to have communications with KGSA on a regular basis. Or in back to 2015, 16, 17, we proposed a suite of ABE schemes with server-aided revocation. Okay, so in our solution, a public server handles revocation on behalf of the user. All right, so users are not involved in the revocation process at all. So that significantly reduces the burden on the end users. Well, those solutions, okay, and because they associate a time with the ciphertext, so a big limitation or advantage of those approach, of the existing approach, is that if we use the technique for protecting data in the cloud, okay, when data is encrypted, we upload it to the cloud, then we need to update the past ciphertext, for example, ciphertext formulated at time t-1 to the current timestamp. So we need to perform this update. Otherwise, revoked users can still decrypt the past ciphertext. But this update process can be done by the server, by the storage, because the storage can do the update, but based on public information. All right, so there's no secret being involved to perform this update, but every ciphertext must be updated and on a regular basis. So just imagine in the storage you have millions of ciphertext, so that can be a huge computational cost on the storage server. So this is the major limitation of those existing solutions for user revocation in ABE systems. Well, another line of research for user revocation is to make use of the after-sourced decryption. Okay, so we also have a number of papers on this, and in this approach, in this so-called verifiable after-sourced decryption, or ABE-VOD, this approach, this solution, each user is given a decryption key and a transformation key, right? So user is given the decryption key, the user's transformation key is maintained by a proxy, okay? So this can be a cloud server, all right? So every user will have a transformation key. When user wants to decrypt a ciphertext, the proxy will take the user's transformation key to do a transformation for the user and to produce a simplified ciphertext and send to the user finally using his or her decryption key to do the last step of the decryption. Well, so this solution, we can make it for user revocation, right? So to revoke a user, the proxy deletes the transformation key. So very simply decline from the transformation operation for the user, then the user can be revoked, right? But the assumption is that the proxy does not collude with user. So this sometimes can be a strong assumption, all right? Well, so the next cryptographic technique I'd like to outline is on searchable encryption, or SE. So SE allow keyword search over ciphertext without revealing keywords and data to the server. All right. Lots of research has been done on SE. However, most of the SE schemes are for single user setting, right? So that means only the holder of a secret key can issue and can produce search queries. All right, so the system is essentially assuming a single user. Well, if the system have multiple users, the multiple users can certainly share the secret key, right? And that is a solution to support multiple users. But sharing of the secret key makes the user revocation complicated, because if one user is revoked, the whole system, the secret key must be updated. That will affect every user. There are also research, but limited research on the multi-user SE schemes. All right, there are several such existing schemes, and multi-user SE schemes, multi-key SE schemes, and recently, there are quite a number of papers on ABE-based SE schemes. Okay. But the problem with those solutions, they have some other limitations too. Among the limitations, the biggest limitation for practical applications is that the search computational complexity is proportional to the number of documents. Okay, so the number of documents in the cloud can be on the millions. To conduct a keyword search, the server have to go through every document. Okay, search through every document looking for the match. All right, so computationally is expensive. Well, in IPsec 2008, we proposed a efficient multi-user SE. Okay, so to my knowledge, this is the probably the only efficient solution ever defined what is efficient, and to SE schemes which support multi-user to multi-user setting. So the multi-user, we can have multiple owners who can formulate the keyword index. Okay, they can upload keyword index and the ciphertext to the cloud. Okay, they can also do this, and they can also have many multi-data users who can issue keyword queries so that the proxy can conduct the search on the in the cloud, and return the ciphertext which contains the keyword back to the data users, right? And no dictionary attack in these schemes. That means if you know the keyword index, you cannot perform a dictionary attack to discover the underlying keyword, okay, hidden within the keyword index, right? Well, the cost of the keyword search is log n. Okay, n is the number of keywords. So this is independent of the number of documents in the storage. Okay, that's why it is efficient. So this is the definition of efficient. And there is a name for this kind of SE. Okay, so such SE schemes are referred to as efficiently deployable and efficiently searchable encryption, okay, in the literature. So EAI SE in short, right? Well, the EAI SE unfortunately suffers from a keyword discovery attack. So this is a paper upcoming CCS, And in this paper, we proposed a attack called leap, right? And using the leap, we did a experiment. So in our experiment, we used the INRA email database, which has more than 30,000 email messages as the document universe. And we used the standard Porter stemming algorithm to extract the 5,000 most frequent keywords from those documents. So as our keyword universe, all right? Well, the attack is assuming the attackers has access to the storage, to the keyword index, to the encrypted document, and also the attacker here. The attacker is the server, all right, and the server knows a small percentage of leaked document, knows a small percentage of the plain text of those document in the document universe, all right. So if we look at some of the examples, so if the attacker, the server, knows 0.1% of the document, and he is able to discover 132 keywords, all right, from the keyword index. And if he knows 1% of the plain text document, he can discover almost 53% of the keywords. And if he knows 10% of the plain text document, almost every keyword can be discovered. So this is a very powerful attack. And in the system design, we have to have countermeasures to mitigate this kind of attack, even if we're using EAI as our keyword search technology. Well, next, I'd like to talk about SBox. SBox is our design, is our proposal for secure enterprise cloud storage system. And so essentially we have to, take certain, cryptographic techniques, and also from the system architecture and the combination of the two to make a system which is, secure and efficient, okay? Well, SBox is designed following the zero trust paradigm, all right? So in particular, we don't trust the cloud storage server to keep our data confidential. So that is our major assumption. And SBox can provide end-to-end encryption, okay, such that data is protected even if the storage server or a user account is compromised. Data is still protected. And it provides scalable access control of the encrypted data, provides secure search of the keyword search over encrypted data, and in future, it can also perform computation over encrypted data, all right? Low operational cost, simple cryptographic key management, and efficient user verification, all right? Well, so the key cryptographic techniques used in SBox are the two techniques I mentioned, okay? The first technique we use is ABE, VOD, verifiable after source decryption. And recall that in this solution, a user has a decryption key, has a transformation key. And the transformation key is controlled by a proxy, right? So when user is revoked, the proxy just delete the transformation key. Well, so now the transformation server in our solution is doing the transformation after source decryption and also user revocation. The disadvantage of the scheme, if you recall, is that it has this strong assumption the transformation server does not collude with users, right? So in the system design, we should make this a realistic assumption, right? The second cryptographic technique we use is multi-user EDESE. Okay, so this is our proposal in IPsec 2008 and support multi-user to multi-user SE efficient. Okay, so efficient, it means the search is log n is number of keywords, but the disadvantage is it's subject to the leap attack. So I just mentioned the leap attack. The server knows a small percentage of the plain text can discover a big portion of the underlying keywords. And in the system design, we have to somehow solve this problem. Now, the challenge in the system design, okay, facing us is how to achieve good efficiency and good security at the same time. Well, so this is the SBox system architecture or a deployment scenario, right? So SBox has a SBox server cluster, okay? And SBox is designed for organizational users. So the organizational users will have an IT department. So the SBox server cluster is managed by the organization. All right. So this is deployed on premises by the organization. And we have the client software for Windows, Linux, Android, and iOS. All right. Data after encryption are uploaded in the public cloud. All right. So in the public cloud, the assumption is that the public cloud storage server we do not trust at all. We don't trust the public server to keep our data confidential. Well, another way to look at SBox is in terms of the operations when data is encrypted and uploaded to the cloud. So at the bottom, we have the SBox client. Okay, the client is doing the encryption. We have end-to-end encryption and decryption. The client have a plain text file which is encrypted, and it passed to the SBox server cluster. The server cluster is controlled by the organization. All right. So this server cluster essentially has three functions. The first function is it maintains a virtual file system. Okay, so the file name is mapped to a pseudonym, and it maintains the ABE access policy. It maintains the keyword index and permissions. So the permissions is the user to have permissions to create a folder, to delete a folder, etc. Right? And so because the SBox server is maintained by the organization, right? So the ABE access policy will not leak information because it is controlled by the organizational server. The ABE access policy does not appear in the public cloud, right? And the keyword index, the search is conducted by the SBox server cluster. That is also conducted by the organization, so it will not leak information to the public cloud, right? So this is how we achieve good security using efficient cryptographic techniques. And the second functionality of the SBox server cluster is to perform ciphertext transformation and user revocation. The transformation is after-source decryption, so that can reduce the computational cost at the, for example, mobile devices. User transformation is controlled by the server cluster, is controlled by the organization. Keyword search is also performed by the server cluster. So what is maintained in the public cloud is essentially ciphertext. Even the ciphertext will not appear as a, with the real file name. So the file name is replaced with a pseudonym. So we have this file name to pseudonym mapping. So whatever is uploaded in the public cloud appears totally random, all right? So this is the how we we achieve good security and efficiency. Well, the server cluster, as I mentioned, this is maintained by the organization, right? But maintained by the organization, we want the maintenance of the cloud server to be as simple as possible. All right. So the Xbox server cluster implementation is using a Kubernetes packaged server components. We did this implementation. So Kubernetes is from Google, which is the state-of-the-art cloud computing technology. So with the Kubernetes implementation technology, it can support easy deployment and management and high scalability. And when you need more workload and more component servers will be added automatically to the server cluster, and also can perform automatic scaling up and down, and also trigger notification to server maintenance crew upon there are failures which cannot be automatically recovered. All right. Well, finally, this is the user interface screenshot of the Windows client. So in this screenshot, we have the each user will have a personal folder, okay, a corporate folder, and within the corporate folder we have, this is the SMU, my university, okay, this big folder. Within the big folders, we can have subfolders. SMC is the secure mobile center. All right. Within the secure mobile center, we have subfolders lab 1, lab 2, lab 3. And each one of those folders is associated with a ABE access policy. Okay, so lab 1, for example, can be accessed by somebody with the decryption key, and that key corresponds to attributes SMU, professor, and SIS is name of the school and admin staff. Okay, so you can access the files in decrypt files in lab 1. Similarly, lab 2, lab 3. All right. So each folder is associated with a access policy. Here we for ordinary users we call it view policy. All right. Well, so let me conclude my talk. And the message I'd like to pass is that many cryptographic techniques have been published in the literature. Okay, but those techniques, they have a lot of novel and nice features, but most of them are piecemeal solutions. So they address one problem, does not address another problem. So the two different techniques may not work together. All right, and they are often limited in usability and limited in efficiency. Now, in the system design, okay, it is extremely important to balance security, efficiency, and usability, right? So to balance the security, a lot of times the cryptographic techniques alone are not sufficient to achieve the balance. So we have to take a integrated approach to seamlessly integrate cryptographic solutions with system solutions. All right, and I presented an example of our attempt to do the balance between security, efficiency, and usability. So our solution we propose is Xbox. So Xbox integrate ABE VOD. Okay, this is for one-to-many public key encryption, and which support efficient user revocation. And we also integrated with keyword search, multi-user keyword search, which can perform efficient search. And with system architecture, right? and to provide good security, efficiency, and usability. Thank you very much for your attention.